back, everyone. It's a pleasure to introduce Kasia, who will talk about cubical quotients of nonproducts.
Thank you. So what I'm going to talk about is joint work with Macarena. Renas was here somewhere, Macarena, and Donnie Wise. And it's a talk about Kasia cube complexes or non-positively curved cube complexes, which are objects that are nice. They're built out of cubes. I'm not going to define them any further. But I drew here a little example, and this is a hyperplane in a Kasia cube complex. So I kind of assume that most people are familiar. If you're not, they're nice non-positively curved spaces. Fundamental group of non-positively curved cube complexes have some nice algebraic properties, but I'm not really going to talk too much about those today. And what I want to start with is sort of the opposite thing to all the nice things. So in a way, like as weird or exotic example of non-positively curved cube complexes. So this is a theorem due to Berger and Moses. That says that there exist non-positively curved cube complexes. In fact, two-dimensional non-positively curved cube complexes with fundamental group pi1 that's infinite simple group. So this is maybe not how usually this theorem is stated. Those examples here, so maybe have universal cover that is a product of two trees. So maybe regular finite valence trees. So this is kind of a particular example of non-positive or Kasia cube complex that is a product of two trees. So this is weird group, infinite simple groups, at least from the point of view of like other, there are a lot of, if you assume some extra properties of non-positively curved cube complexes, their fundamental groups become of very different kind. And so what I want to tell you about today is a theorem that says that this is sort of the only situation for non-positively curved cube complexes to have such exotic fundamental groups. And so let me make it precise. This is the theorem. So I'm going to assume that I have G, this fundamental group of a non-positively curved cube complex. Which is compact. And such that its universal cover is not a direct product of two cube complexes. And the statement is that then G is not simple, but in a stronger sense, G has admits a proper quotient G bar with the same properties. And with the same properties, I just mean everything that I just assumed about G over here, so that it's a fundamental group of a non-positively compact, non-positively curved cube complex whose universal cover is a non-product. And there are a lot of ways of choosing this proper quotient. So if I, for example, if I pick some finite collection of elements in G, I can ensure that those elements survive in the quotient. So we can choose G hat, this proper quotient, such that the images of G1 to Gn in G hat are not trivial. And so before I actually move further, here, the assumption is that this universal cover is not a product. I wrote it as non-product because I'm going to actually need something a little stronger than just saying that X tilde does not decompose as a product. I will mean that there is no invariant subcomplex of X tilde that decomposes as a product. So this is just what I mean when I say non-product. If no pi1 of X invariant of X tilde splits as a product of unbounded complexes. So really just, or one way of thinking about it, if you already know that your action of the fundamental groups of X is essential, then this is just not splitting as a product. But otherwise, kind of example that you can have in mind, if I have a product of two lines that say cover the torus, this is a product, but there is easy way of changing it a little bit to make it not a direct product of two complexes by attaching extra edge at every vertex that correspond to just like in the quotient attaching extra edge. This is not a product anymore, this Kasia Jankiewicz complex, but it is morally a product, so I want to exclude this kind of examples as well, because of course this doesn't change anything about the fundamental group of this space, so it's kind of a stupid way of making universal cover not a product. So this is also what's going to be excluded when I say a non-product here. Yeah?
Do you know whether under your condition the group is symmetrically handled?
Yes. And so if you're following here carefully, you might be like, oh, this is actually, I'm telling you, this group is not simple, but this is already known because it is a cylindrically hyperbolic. And so really what is kind of new and non-trivial in this, or well, I'm not saying that's trivial, that also follows from work of, I guess, Kaprastegui and rank rigidity and like Austin's like isomorphic hyperbolicity. But really this part where I say that this quotient has the same property, so in particular, yeah, it's a fundamental group of a non-positively curved cube complex, compact non-positively curved cube complex, I started something that's compact here, is kind of the difference. So in other words, I could also change the assumption a little bit. For example, I do not need to assume compactness, and I still get quotient in the same class of groups. And so this version that I'm presenting here is the class of groups is compact, fundamental groups of compact non-positively curved cube complexes, and I guess that are non-products. Yeah, thank you for the question. Okay, so this is the theorem, and I'm going to spend most of this talk telling you about the techniques. And so the main tool that we use to prove this theorem is cubical version of small cancellation theory. And so this is cubical version of small cancellation. So maybe starting with kind of classical small cancellation, I'm gonna kind of in parallel tell you about notions from classical small cancellation and how they generalize to the cubical case. This is classical. That goes back to really to ideas of Dane from early 20th century and some other names, Tarkovsky, Grinlinger, and kind of more geometric view due to Linden. This is all early, mid, like 70s, like all 20th century, pretty well, classical. And the version, the cubical version is due to Wise. Okay, so let me tell you what this is. So to talk about small cancellation, we have to work with group presentation. So maybe I'll use two sides, classical and cubical, and then I'm going to start on the classical case. Well, group presentation is just a set of generators and relators, but we usually, if we want to think about it geometrically, but we visualize it as a maybe wedge of circles. Let me just grab enough colors. One circle per each generator. And we think of relators as disks mapping with whose boundaries mapping to the wedge of circles. So maybe it looks like this. And of course, we can have more relators. And so on the cubical side, I'm going to try to look at similar geometric picture, but instead of just assuming that I have wedge of circles and cycles mapping to it, I'm assuming that I have just arbitrary cube complexes and local isometries. So those are all non-positively curved cube complexes. And each yi comes with a local isometry to x. So in particular, a map that induces embedding of the fundamental groups. And when I write something like this, I mean, this is really just a list of complexes. What I mean when I say that G is a group defined by this, I mean that G is, you can either write it as product of pi1 of x modulo this normal subgroup generated by fundamental groups of each PYIs, of each YIs induced by this embedding. Or another way of writing the same thing is by constructing an object whose fundamental group this is, and I'm going to denote it by x star, and I'm going to use a little bit of space here to draw it. And so what you should imagine is like we have our x, and we have yi's somewhere in x, and we're just looking at a cone over each yi. So x star is a space obtained from x with cones over yi's attached. And so if we look at this kind of space, and we look at its fundamental group, this is exactly, it's going to be the group, this quotient. And going back to this situation, this is really not like, this is really a generalization of the situation if we consider this object to be x and each of these cycles to be yi, and attaching disk with prescribed boundary map is exactly the same thing as taking a cone over that boundary cycle.
So you don't know that X star is a non-positively curved cube complex itself?
No, I'm not. So this is something that consists of a non-positively curved cube complex with a bunch of like hats attached. So a bunch of like those. If you want, you can put sort of stellar structure on those cones so each is going to be a cone over a cube, but there is no any natural cubical structure on this object. And in particular, I do not claim that the cube complex that I will be constructing for some kind of groups like this cube complex that it acts on, or that is fundamental group, but it is not going to be homeomorphic to this object. Okay, so once we have group presentations, to talk about small cancellation, we need a notion of pieces. And so again, I can do it two-side, classical, and cubical. And in the classical case, if we think about our presentations geometrically, pieces will be just overlaps of a pair of relators. And so it really makes most sense to look at it in the Cayley complex. So in the so maybe, yeah, so if I have, looking at the Cayley complex, two relators, so two true cells that attach along boundary, I'm going to call a piece anything that lies in this overlap. So, overlap of two relators. And we can try to do a similar thing on this side. And so I'm going to be looking at universal cover of my X star tilde. So X star, again, is this object. So it has it's a cube complex, non-positive complex with hats. And so when I look at the universal cover of this object, like whatever is in the hat is like already made simply connected by the hats. So there is still, probably some unfolding coming from the rest of the cube complex, but it's still going to look like it has, so it's presumably like infinite cover of this object, and it has, copy of it, many copies of each hat. And so now I just want to look at overlap of those two yi's. You can think of like also them having hats, but you can also just look at those cube complexes. So if I now, take universal cover of this and forget about hats, it's a non-positively curved cube complex, probably infinite non-positively curved cube complex. And so I can sort of forget about the hats, look at this intersection. Now, intersection of those two things, since they were not just cycles, they were some cube complexes, can be more than just a path. It can have, some cubes in it. So I'm going to call a piece just any path. And every time I'm going to say path today, I'm just going to mean combinatorial path. So P, this one I'm going to call cone piece. This is any path in the overlap of like those two lengths of those relators in this universal cover. And so I said here cone piece because this is actually not the only type of piece that we will consider in the cubical case. And to kind of maybe try to justify a little bit why there should be more, you should expect more pieces, let's consider an example where I have two of those relators, and they're not quite touching, but they're morally touching, meaning that there's just like grid connecting them in this way. So this is something we can't have here, obviously, because there are no squares, no cubes. But they're still like in some kind of coarse way, they're overlapping. And so we want to also consider pieces in this situation, and specifically, I want this path to be a piece. And actually what I'm going to define is the following. So actually, for this definition, I'm going to forget now about this part. This was a little bit just to convince you that there should be more things. This is not the only reason. But now, if I have a relator and I have a hyperplane, so this is a hyperplane, so this hyperplane is not entering yi, but it's carrier, so the union of the cubes that carry this hyperplane are touching yi, then any path P, so P here is we're going to call wall piece. And so this is any path in the overlap of yi and carrier of a hyperplane, so by n of h. So I have more colors I haven't used. This is n of h, the carrier of the hyperplane. And so this is the second type of pieces that I'm going to be considering. Any questions? Okay, so once we have pieces defined, we can talk about small cancellation, conditions, and I guess maybe again I will, well, maybe I'll just say that, we'll again say that our presentation, so in the classical case, we say that this presentation is C prime alpha, small cancellation, if, so alpha here is going to be a number between 0 and 1. And this condition tells is so that any piece is at most alpha, has length at most alpha times the length of whole relator, where P is a piece contained in Ri in the relator. So it's a subpath of the boundary path of Ri. And similarly here, we're going to say that this is C prime alpha small cancellation. We want to say something similar. Of course, it doesn't quite make sense to look at the length of a relator, since our relator is a cube complex, but we can look at essential loops in in yi. So if I have an essential loop and I look at a P that is a piece contained in that loop, so some subpath that is also contained in some other relator or in some hyperplane carrier, I can again compare their lengths. So, so this is our all paths that I'm looking at. And also in both cases, there is also, this is called metric small cancellation condition. There is also non-metric small cancellation condition, which doesn't, which doesn't look at the length, but it still tells us that we need many pieces to complete the whole relator. So here I'm saying that Ri cannot be expressed as a concatenation of less than n pieces. So here n is an integer, of course. And we have kind of the same condition sort of here with, appropriately adjusted. So here we would say that this cubical presentation satisfies Cn small cancellation condition if no essential loop in any yi can be expressed as a concatenation of less than n pieces.
So the war piece does not play a role in your definition?
Oh, sorry. So when I say pieces here, I mean either cone or wall pieces. So I defined, cone and wall pieces. When I just say pieces, I'm just considering all of them pieces. Yeah, thank you. That's a good clarification. Okay, so some properties. And so maybe I'll move more over and write classical here. And I'm not really gonna, let me just, I'm just gonna indicate if there is a version, but I'm not gonna necessarily state it very precisely. There might be extra assumptions. But okay, one thing that is like really kind of easy observations if we just compare C prime alpha and Cn conditions, if we take alpha equal 1 over n, it implies C, I guess n plus 1. So if our pieces are less than 1 over n of the length of the whole thing, then we at least need n plus 1 of them. Maybe this is 0. 1. So really where this definition in the classical case came from was as a class of groups that have word problems solvable by Dane's algorithm, basically. So I guess the original Dane solved word problem for surface groups, and then it was observed by those people that really that proof is much more general than just for surface groups. And that's where that class of groups came from. And so this is going to be for C prime 1 over 6. So if alpha is equal 1 over 6, then solvable word problem, which is, I guess, due to Gridlinger's lemma, which is sort of in the kind of geometric formulation, sort of classification of disk diagrams over those kind of presentations. And so there is some version, like, let me just write, there is a translation of Gridlinger's lemma. In the cubical case that I'm not gonna explain any more about. There's version by Weiss and version by myself in paper that is after this paper, even though years suggest otherwise. Second property, so it's also for C prime 1 over 6, is hyperbolicity, which is, it was actually kind of one of sort of two types of groups that inspired, I think, notion of hyperbolicity due to Gromov. On the other hand, having fundamental groups of negatively curved manifolds. So I guess those are groups that were hyperbolic before hyperbolic was a thing. Gromov hyperbolic. And there are versions of this kind of theorem. So under some small cancellation condition, you can also prove hyperbolicity of cubical presentation, but of course, you probably want to assume that complex that you start with X is hyperbolic to be able to get anything like that. And so there is version, metric condition version by Weiss, and there is another version in another paper of Macarena, Johnny, and myself for non-metric small cancellation condition. There are also results that tells you that if you additionally assume that your relations are not proper powers, then your presentation is aspherical. So in particular, that presentation complex is a K-pi1 space for the group. So groups are two-dimensional, and there are also there are some versions of that statement in the cubical case due to Macarena, where in particular she can kind of estimate the dimension of the group based on like the dimension of the original data. And one last thing that I want to mention here is this is also just 1 over 6 condition that, and this is due to Weiss in 2004, that groups that are C prime 1 over 6 small cancellations are co-compactly cubulated. And this on this other side is a theorem that I'm going to write over here now that can be viewed as a version of this in the cubical case, and which is in particular something that we use here, and specifically in this part where we're getting quotient that is co-compactly cubulated. That is the fundamental group of a compact, non-positively curved group complex. So I'm going to say this theorem and explain some words, and then I'm going to kind of tell you a little bit more about the outline of this first theorem that's on the left. Here is theorem 2. So if I assume now that I have my group that is given by some cubical presentation, I'm assuming it's compact, which means that all of those, like both of those complexes are compact. And satisfies sufficiently good small cancellation conditions. But I'm not going to actually tell you which ones. Then I want to say that it's co-compactly cubulated, so it's acts co-compactly on a cat-zero cube complex, but actually I do have to write another assumption, and the assumption is about y. So I'm assuming y is not just any non-positively curved cube complex mapping to my non-positively curved cube complex X. I'm assuming it is a superconvex pseudograph, and I will explain in a moment what that means. And then I can conclude that this group, given by this cubical presentation, acts co-compactly on a cat-zero cube complex. I'm going to use this side of the board to now explain these words. Okay, sorry, I was sitting in this part, so I know that you can't see when the board is behind. So maybe I'll just do it anyway. Sorry. I will move it higher in a second. Okay, so I want to tell you what superconvex pseudographs are. So, well, it's a pseudograph that's superconvex. So let me start with a definition of pseudograph. And this is just a, so I must, this is a non-positively curved cube complex in which all the hyperplanes, I guess immersed hyperplanes, it's a non-positively curved cube complex, so we can only hope for immersed hyperplanes in general, but here we're actually saying that they are contractible and embedded. I mean, I guess, I don't know if it would make sense to say contractible if they were not embedded. Anyways, so here is what you should picture. You should picture it something that looks sort of like a graph, but it's like maybe thickened a little bit. So, actually, so this is an example of a pseudograph. So all the hyperplanes here are contractible. There are a couple of them. But it still sort of looks like a graph. And now superconvex. So if I have a map of non-positively curved cube complexes, that's a local isometry. It is a fact that if we look at universal covers of y and x, this map induces an embedding of the universal covers. And so we're going to say that this map is superconvex if the induced map that we have of the universal covers, for one, is an embedding of a convex subcomplex. This is convex, but we also assume more than that, and we can consider any bi-infinite geodesic in X tilde. We call it gamma, or, and if that geodesic is sort of parallel to Y, so this is in X tilde, so it's not necessarily contained in Y tilde, but if it is parallel, meaning it's contained, you can say that it's contained in some neighborhood, some R neighborhood of y tilde. So maybe, okay, I said parallel, but like you should just, yeah, it's just contained in some R neighborhood. You don't have to necessarily imagine something contained. It actually implies that it is already contained in y tilde. So y tilde sort of, if you have like, yeah, so this is the condition. So this is sort of a picture. I have y and, you know, it basically tells me that I cannot have gamma that is just stays in some neighborhood without being contained in y tilde. And there is also an equivalent way of phrasing this condition when you make some mild assumption on x. So if we assume that, and y, so if we assume, so equivalently, and this is when x is locally finite, and y is compact, and so in particular, those are this is the situation that we are assuming the theorem. In this case, this condition becomes the following condition, that there exists a bound on the length of combinatorial strips of this form. So this is, so what is happening here? This is a combinatorial strip that is not contained in y tilde, but one side of it is contained in y tilde. And so if its length is L, the condition here, such that for every strip like this, L, small l, has to be bounded by capital L. And now, I'm just going to move it up so you can see it. And hopefully you can still see this. So this is, yeah, so this equivalent condition doesn't, you know, in the first condition you kind of have to be looking at sort of big, you know, bigger and bigger neighborhoods possibly, because there is this R that I guess I didn't write a quantifier for, but if there exists R such that gamma is contained in the neighborhood, this condition implies that gamma is contained in y tilde. This condition is kind of more local. You only have to go one away from y tilde, so maybe it's a little easier to visualize. And so I wanted to very quickly just, you know what, go back there. So very quickly, what is a non-example for superconvexity? If I take X, which is product of two graphs, so for example, this is one graph and this is the other, and I take product and I get, you know, my X, then of course, each of those graphs maps via local isometry. So gamma I maps via local isometry to X, and it's a graph, so in particular it is a pseudograph. Pseudograph is just a generalization of a notion of a graph that is not superconvex. Because if you kind of look at this product of two graphs, look at its universal cover, then, you know, like you would have product of two trees. Each tree, of course, maps to the product of those two trees, but it has like infinitely many kind of parallel copies. So you would see those infinite geodesics that are in some R neighborhood of your one copy of a tree, but it is not contained in that tree. So it does not satisfy this superconvex, the definition of superconvexity. Okay, so I have 5 minutes. Is that right? No. Yeah. I'm just confused because there are two ones. Yeah. So let me just tell you a little bit about how does this relate to this theorem, or what is really this structure here. Just use this last board. And so in our original theorem, so I'm going back now to the original theorem where we assume that we have a compact non-positively curved cube complex that is a non-product. And the first step here if I have X whose universal cover is a non-product, then using that, really mostly using work of Kaprasik of rank rigidity, and in fact this is equivalence here, is that we can construct superconvex rank 2 pseudograph Y that maps to X. And once we have a superconvex rank 2 pseudograph, this is, if we look at this presentation with X and Y, it doesn't have to be small cancellation, but what we can do, we can always pass to, so here, since I'm assuming, so by rank of the pseudograph, I just mean rank of the fundamental group. Every pseudograph has free fundamental group. This is, I guess, a fact. So, so this is going to have a lot of sort of, just like graphs, it's going to have a lot of other pseudographs mapping to it by local isometries. So we can find something else, some other, for example, rank 2 object. Superconvexity is always going to be preserved here, and being a pseudograph as well. And so we can choose further Y prime that maps to Y and maps to X, that is going to be still superconvex rank 2 pseudograph. We can choose it so that this presentation with X and Y tilde satisfies any small cancellation. Let me just write good small cancellation conditions. And so once I have something that satisfies small cancellation conditions that I requested in this theorem, they didn't tell you what they were, we can, we know that it's going to be acting co-compactly, but we can also make this choice, so maybe I should try it, perhaps further choice can also ensure that this action is not only co-compact, but it's free. Maybe. So this is kind of using my theorem too, but also using a little more to also ensure that the action is free, and we can also ensure that what we get here is a non-product. And I am ready to stop, even though I still have 25 seconds. Thank you.
Any questions?
Do you have?
Oh, sorry.
You want to start?
I was going to say, do you have any applications where you apply the result over and over again, and then you can get some interesting grades?
Yeah. So yeah. Of course. Yeah. Since we are starting with something and we're constructing quotient that's of the same type, we could think of we could apply it again, and we don't know. There's nothing we can say. In fact, we don't actually know whether you're going to be getting something that's not abstractly isomorphic. I mean, it feels like there are a lot of choices, so you should be able to do it. But we haven't actually found any kind of thing that could distinguish those quotients. So we have thought a little bit about it, but we don't have anything to say about what would happen if you look at repeating this procedure. But of course, that's a very good question, natural thing to look at.
So my question was a little bit related, so I was wondering if you have a WPD element or something like that.
If you have what, sorry?
If you have a WPD element or like a Morse guy or something, if you take a big power of it, can you seek your Y?
So if you take a power of it, it's not going to be, we're not going to have a free action, so it's not going to be a fundamental group, but this is not what we, yeah.
So you cannot kill.
I mean, you could do it, of course, but
yes,
like,
of course, yeah.
but like, I guess the way we're doing it is like to kind of not just, yeah, take, yeah, but like but you're maybe like thinking, what if I just take, sort of like knowing how you construct quotients before, if I take some like specific element,
Right.
WPD element, and whether if you take power of it, if we could, for example, say that like it's compact, yeah, we don't know that, and I feel like, yeah, like I feel like a priori it's like you don't know what to look at there, but if anyone knows how to do it, that would be interesting. But yeah, I don't think we know how to pick a specific element without. Yeah.
Do you have control on the coherence dimension of the quotient?
I mean, that's gonna be like, I think here, this result of Macarena, where so I'm not gonna state you exact assumptions, but I think she like has the way of estimating the dimension in terms of like dimensions of X and Y's and maybe something else, I'm not sure, but yeah, so she can tell you all the details. Yeah.
So
Yeah.
maybe this is a silly question, and maybe you mentioned this and I missed it, but if you have something satisfying one of these sufficiently nice cubical small cancellation conditions, can you solve the word problem in the fundamental group?
I believe so.
Any more questions? So let's thank Kasia again.